Yes, sir.
Okay. So, hi, my name is Rohit. I am the TA for the course Wave Optics, and this is the extra session of this course. So, uh, today I'll discuss the Fabry-Perot interferometer, one topic that we missed, and we will see some examples. So this topic is not very the problem on this topic will not be very complicated. It's a very There are two or three very simple formula, and the questions will be straightforward, but there are many derivations in this topic, long derivations that I will not go into. Rather, I will just uh, like intuitively I will write down the formula and explain it, what does it mean, and I think that will be enough. You don't need to go through all the derivation. Anyway, it cannot be covered in 1 hour, so let's see. But yeah, for solving the problems we don't need those derivations anyway. uh, I will do some derivation where it is required, but not all of them. So okay. So first we before we study the Fabry-Perot uh, interferometer, we need to study the multiple reflections. Okay. So what happen when there are multiple reflections from parallel plates? Okay. So what I mean is, suppose you have two parallel plates like this. Okay. And so the medium inside the plates, its refractive index is n2. Outside medium, the refractive index is denoted by n1, and there is an incident light. Okay. Which has amplitude a naught, and this is the normal, and this is the angle of incidence theta 1, and the sorry yeah, the refracted light goes like this angle is theta 2, and there will be a reflected light like this. Its amplitude, let's call it a1, and then again it will reflect from here on the bottom, and it will transmit also. So this interface, this is this is basically a slab of you can think about another medium. Okay. So like when we studied the thin film, we had something like this, right? And again there will be transmitted light here, reflected light here, and this process goes on, right? This is A2, A3. So one incident light with A naught on this parallel plates, on a medium, gives us many reflected lights, and so this is a case of multiple reflections. Okay. And there is a term called reflectivity. So reflectivity for any surface is the ratio of the amplitude of reflected light and the incident light, okay, squared. So here the reflected amplitude will be the sum of these individual amplitudes. Okay, and this is given by this formula. So I'm not deriving this formula, okay, but I will say what everything is here. So okay, so this is the reflectivity of a surface. It is denoted by R, okay, and F here is given like this: 4 R naught 1 minus R naught square, where this R naught is the reflectivity of individual reflected lights. So for example, this A1, A2, A3 that you have, so they are basically their reflection coefficient we denote by R1. So and we assume that all of them have same reflection coefficient. So what I mean is, so R1 is basically A1 by A naught, R2 is A2 by A naught. Okay, these are called reflection coefficient, and we for now we will assume this is they are, I mean, their square is very similar. Okay.
Sir,
Yeah.
what is delta H?
Sorry. Yeah. I am going at it. So this is called coefficient of finesse. Okay. This F. It has an important role to play. I'll later we will see. Now, this delta that is there, it is basically the phase difference. Okay. So, phase difference between two reflected light, like A1 and A2, and then A2 and A3. All of them will will have same phase difference, right? Because they are traveling the same. So A1 and A1 is this. A2 is traveling an extra path here, right? This path that it is traveling an extra path, and similarly A3 is traveling an extra path compared to A2, okay, which is similar to what A2 is traveling compared to A1. So the path difference between A1, A2, A3, consecutive path differences, they are same, and so the phase difference will also be the same, which is given by 2 pi by lambda into path difference. And this path difference, if you calculate, so 2 pi by lambda, and this path difference will be n2 h cos theta 2, okay, where h is this distance, this vertical distance. Okay, so cos theta will be h cos theta will be this distance here, and since it is it into 2, because it is traveling 2 times, and since it is in a refractive index of n2, so this path difference will be multiplied by n2, right? So finally you will get 4 pi into h cos theta 2. So, and divided by lambda naught is the wavelength of the light in air or in vacuum, basically. Okay, so the path difference here that let me label it. So if this is O, this is A, this is B, so the path difference here is basically OA plus AB, okay, which is same, so it is just 2 into OA, which is 2 into N2H cos theta 2, okay. So that is what we have written here. So this is the phase difference, okay. and so reflectivity has this formula. But uh, here most important thing is this coefficient of finesse, okay, as we will see later. Now there is similarly, you see that there are transmitted waves also in the bottom, right? And this is also important. So there is a transmittivity, okay. So this transmittivity is basically square of the transmitted amplitude divided by incident amplitude, and this is given by this formula, okay. And you can see here that if you add the reflectivity and transmittivity, you get 1, okay. So if you add this and this, you will get 1, which makes sense, right? Because either your light will be reflected or transmitted, so it is just the relative thing that if it is more reflected, then reflectivity will be more, transmittivity will less, and vice versa. But there can be a case when the transmittivity is equal to 1 and reflectivity will be 0. So all of the incident light, okay, will be transmitted. So when does that happen? Can you say from this formula? When do you get t equal to 1? Any clue?
when delta is 180.
Yeah, basically when the phase difference is 0 or 2 pi, so basically
Right.
2m pi, right? So that
Yes, sir.
sine theta is just 0, and you get uh, transmittivity equal to 1, right? So this is the basis of this Fabry-Perot interferometer, as we will see. So Fabry-Perot interferometer, we need this condition, okay. We need the full transmit, like we need the incident light to be fully transmitted. We don't want it to be reflected. So this phase difference is very important, okay. Now, yeah. Also, so this is when full transmittance is there, like all the incident wave is transmitted. But we can also see that when you have half of the incident wave transmitted, okay, like when the t is equal to half, so instead of 1, when it will be half, so let assume that it happens at an angle, either plus minus some angle delta, so yeah, it is delta, I don't know how to say it, but yeah, some small angle, okay, divided by 2. That is what I mean is, if you look at this graph and look at the transmittivity as a function of this phase difference. So as we saw above, at 2m pi we will have t equal to 1, right? So you will have a sharp peak here like this, okay. Now we are looking at when t is equal to half, okay. That is so what happens at t equal to half? So t equal to half, we are basically looking at this point, right? So let me make it little broader for to be visible. Okay, and this is the 2m pi where we have transmittivity equal to 1. Okay, but at half, when the transmittivity is half, we have this width is this small angle, okay, delta. Okay, and this is called full width at half maxima, because it is the width of this distribution at half of the maxima. Okay, so when does this happen? We have assumed that let it happen at some angle delta delta delta. Okay, now we can put this in this formula. Okay, and so on the left hand side you have half, on the right hand side you have 1 plus f sine square 2 m pi plus minus delta lambda by 2, right? So if you calculate it, you will get basically sine square delta lambda by 4 is equal to 1. This you will get. Okay, and now you can assume that this angle, this phase difference is very very small, so that you can approximate the sine delta lambda as sine delta as delta. So at the end you get this angle equal to 4 by square root of f. So this is a very important formula. Okay, and this f is what? If we wrote over here, right? This is the coefficient of finesse, which was given by 4 r naught and 1 minus r naught square. So if you put it here in this equation, you will get it in terms of r naught. Okay, so this is another useful formula. Okay, now what this formula says is, if you have now the transmittivity as a function of delta, okay, if you increase your f, the coefficient of finesse, your width decreases. Okay, so if I can draw it for two different values of f, so suppose this is for f equal to 10, then for a larger value of for a smaller value of f, you will have a broader peak. So this will be like f equal to 5. Okay, and so on. So this width depends on the coefficient of finesse. Okay, and the coefficient of finesse is basically, it depends on the reflectivity of the individual reflected lights, right? The A1, A2, A3. Which makes sense, right? Because if there is more reflectivity, then you have more like if the reflectivity increases, f will increase, okay, and this and if is increasing, this width will decrease, okay. So you get narrower and narrower peak. Okay, so yeah, so basically the width decreases as the coefficient of finesse increases. So yeah, just remember this. So this is an important formula that we will use later, okay. Any question or any doubt?
Yes, sir.
Yeah.
Uh, I wanted to ask that what is the physical significance of this reflectivity and transmittivity, etc.?
Yeah, so that's what I showed here, right? So what is reflectivity? The definition is just this, okay. So it is the square of the amplitude of square of the ratio of the amplitude of reflected and incident light, okay. So that means if reflectivity is more, then the light incident light is reflected more, right? So r plus t should be equal to 1. Now if r is equal to 0.8, automatically t will be equal to zero point 0.2. So your light has reflected more than it has transmitted, okay. Or if r is equal to zero point 0.2 and t is equal to 0.8, then it has reflected less than it has transmitted. Or you can have t equal to 1, r equal to 0. That means all of the light has been transmitted, okay, and none of it reflected. Or you can have t equal to 0 and r equal to 1. That means all of the incident light is reflected, none of it got transmitted, and it all depends on the phase difference, okay. Phase difference and this coefficient of finesse,
Yeah. Okay, sir.
okay. So this is the physical significance. And for the Fabry-Perot interferometer, we need this condition, okay. We need t equal to 1. So that's why we are studying. And then we wanted to look, okay, where does this the transmittivity drops to half, okay. We wanted to check that phase difference, and for that we got this formula. So it drops to half when the phase difference becomes 4 divided by under root of f, okay.
Yes, sir.
Okay,
Sir, one more thing.
yeah.
You wrote like R1 is equals to A1 by A naught
Yeah.
on the. Then you have written that R1 square is approximately equal to R2 square. Why that?
So yeah, so basically what I'm assuming is that all these uh, I mean R1 maybe its amplitude is little bit greater than R2, okay, but since you are squaring it, uh, it will be approximately equal to R2 square. So I mean this is the assumption that has been used to write, to write this coefficient of finesse. Obviously it is not true, because you will have, you know you are losing some amplitude here when you are, I mean when this uh, because here you have a transmitted light, right? So it is not true that A1 should, I mean it is not true that the ratio of A1 and A0 should be equal to A2 and A0, but it is an approximation that, that works here basically, but
Okay,
it's
sir.
not accurate, yeah. it is an approximation. It is not fully accurate. So it is not equal to. It is you can say it is approximately equal. Okay. The
Yes, oh
it
yeah.
does not
Okay,
it,
sir.
it does not drop too much. So that's why we assume that it's almost equal. Okay.
Yes, sir.
Okay. Now so now we can move on to our favorite Perot interferometer, or so Fabry-Perot interferometer is a basically is a extension of something called Fabry-Perot etalon. Okay, so Fabry-Perot etalon. So what is this device? So basically you have these two plates arranged like this. Okay, and this is your incident light. It goes inside, it gets multiply reflected. Okay, and then you get output, I mean lights, and then you use a convex lens to focus this at one point. Okay, on the screen. So I think there is some message. The t versus delta graph will again have value 1 at delta 1. uh, Delta equal to, not at delta equal to 1, but at
Okay.
2 m pi plus 2 pi. Here again it will have a peak equal to 1. Okay. Is it fine? Yeah, delta equal to 0. Yeah, 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 obviously, yeah, delta equal to 0 also. Yeah, true. So I have written a general case. So yeah. Okay. Now yeah, this Fabry-Perot etalon. Okay, and so this is what we have. And now what we assume here is that these plates, uh, yeah, there is no reflection. Okay, so there is no reflection, like there is no transmission on that side, on this side. Okay, so there is no transmission here. Okay, so everything is basically transmitted on the other side. Okay, and we know the phase difference when it happens, it is given by 2 m pi, right? When the phase difference is 2 m pi for t equal to 1. So this Fabry-Perot etalon only works when you have adjusted it. So basically this h you have to adjust, right? And you adjust when you get this condition of 2 m pi phase difference. Okay, and so from here you can write, and also now we are assuming that the medium inside this cavity is basically air. So n2 is also equal to 1 n1, so n2 is removed from the formula, and you can write, you can rearrange it to write the cos theta 2, which is just equal to m lambda naught by 2h. Okay, and now so for simplicity we can study the normal incidence, so that this light that we are putting here, they are normal to the plate. So we now assume theta equal to 0, and then this formula will give you 1 by lambda naught equal to m by 2h, and you can multiply c, speed of light, on both sides to get this formula. And c by lambda naught, you know, this is the frequency. Okay, so uh, and there is an index here m. So these are called the modes, transmission modes. Okay, modes of the Fabry-Perot cavity for transmission resonance. So this t equal to 1 criteria is basically we call resonance. Okay, because all of the incident light is transmitted. So and these frequencies are different modes of the Fabry-Perot cavity. So what does this mean is, suppose now you have suppose now you are throwing many suppose now you are I mean, you are basically throwing a light containing many frequencies. Okay, or a distribution of frequency, a spectral, having a spectral width. So only these modes will, will be appear uh, on the screen. Okay, which have this condition. So what I mean is, let me show you. So take a Fabry-Perot. So for an example, this distance, take it 10 centimeter, okay, between the plates. Okay, and suppose you have a spectral width like this. So this is your incident light. It has a central frequency, and there is a spectral width of 7000 megahertz. Okay, and its central value is 6 into 10 to the power 14 megahertz. Okay, so this, if you have this kind of light, which is, which you can assume it like a normal so the white light that we have, it has a distribution of frequency, right? It contains many different frequency. It is not just one frequency. It is not a monochromatic light, right? So for that kind of light, uh, first of all we can calculate what is the spacing of two adjacent modes. Okay, so what I mean is, basically this is like adjacent mode means for m plus 1 and m. Okay, so that we can calculate from this formula. So m plus 1 c by 2h minus m c by 2h, which is equal to c by 2h, right? So this is the basically frequency spacing between two modes. And if you put speed of light number here, 3 into 10 to the power 8 meter per second, 2 into 10, we are taking h, value of h is equal to 10 centimeter. You can calculate it. It will be like so 2 in 1.5 will be go there, so it will be 1500 megahertz. Okay, so now you can see, if you have this kind of light which has a width, a spectral width of 7000 megahertz, and you are incidenting it on a Fabry-Perot etalon. Okay, so it goes multiple reflection, and on the output what you will see are basically different peaks. So you will see one peak here, and then there will be other peaks, and the distance between these two peaks will be 1500. So this will be 1500, this will be 15. Now you tell me why I have shown only 5 peaks here. Any idea? So this is the width, and the total width of the incident light was 7000. Okay,
Yes, sir.
so why 5 peaks only? So you can just divide it, 7000 divided by 1500, right? What do you get? 14 by 3, 4.6 or something, right? So if you convert it into integer, you get 5. So this 7000 width that you had, you have to, because the spacing between the two peaks should be 1500. So 1500 here, and then again 1500 here, right, between these two. So here you have in total 3000, and here also you have in total 3000. Okay, so in total peak to peak you have 6000 spread, right? Beyond that you don't have the incident waves here, right? You have incident up to like 7000. So this should be 7000. So that's why you get only 5 peaks. Okay, you understand my point? So between the two modes you should have a gap of 1500 megahertz, and the total range that you have of the frequencies is 7000 megahertz. So you will, in total you will get only 5 peaks.
But sir, it's not like it's not 7, it's 4.6. It's not 5.
Yeah, it's
How
not
come we have
it's not 5,
5?
but it's closest to 5, no? And you can see, that's what I'm saying. So from its end to end you have 7000. Okay, and from this peak to the second peak you have 1500, then again from the second to third peak you have 1500. So 3000 on one side, 3000 on other side. So total the lowest peak, the peak to peak of this last mode is 6000 megahertz, and but you have 7000 megahertz. If it would have been 5000 megahertz instead of 7000 megahertz, then you would have got only 3 peaks. So you have to like check it properly. You got an idea?
Is it like in that range how many peaks we can means like how many peaks would show up? How many peaks can be?
So you have 6000 megahertz of sorry, you have 7000 megahertz total range, and in the output there should be peaks with separated by 1500 1500 megahertz, right? So how do you distribute 1500? I mean, how many peaks will be there separated by 1500 in a range of 7000 megahertz?
Yep.
6 peaks, right? It's a simple problem.
Okay, okay, sir.
Okay. Okay. Uh, and also you can calculate the value of m. So what will be the value of m here? How do you calculate? So for these modes, what is m? So m is given by this formula. This formula you can use to calculate m, right? So m is this divided this into 2h divided by c, right? So you can calculate it for the central one, and for the central one the frequency is given, which is 6 into 10 to the power 14 megahertz into 2 into h divided by c. So if you calculate it, it will be around 4 lakhs. Yeah, it will be 4 lakh exactly. So these different peaks that you have that you see, they will have so this one is m minus 2, m minus 1, so m minus 2 is 39998. Then you have the second one will be 39999. The third one that we have calculated it 4 lakh, then you have 4 lakh 1, and then you have the last one 4 lakh 2. So these are the order of the these are the mode number, you can say. Okay, we used this formula. So this is a very simple and very effective device. So if you have a frequency, I mean if you have a light having a continuous frequency distribution like this incident, it will it will separate it into different modes. Okay, so it has a application on resolving different components of light. That for that we need the Fabry-Perot interferometer. So let's see how Fabry-Perot interferometer works. So it is nothing but the above device, but now this distance that you have, this h distance, now you make it variable. Okay, so this now changes. So you have you don't have a fixed distance, you change it and you see what happens. Okay, so to see what happens, let's write the phase difference formula again, which is 4 pi mu naught divided by c, and instead of h we now write h naught plus x. Okay, so h naught is the initial distance and x is the distance that we change. So these plates initially at h naught, but then we change it to some distance x. Okay, and we see what happens. And let's use a light having central frequency the same above in the example. Okay, so this, if you take h naught odd, and also in h naught we will use the 10 centimeter as above. So if you take h naught out of the bracket, we will get 1 plus x by h naught. Okay, so if you calculate these, everything is here given. H naught is given, mu is given, frequency is given, speed of light, you will get 8 lakh into pi. So pi we are keeping as it is. and in the bracket you will get this. Now what we know, so we know that you need delta equal to 2m pi for the resonance condition, right? Resonance means t equal to 1. This we know, right? And for, so initially when it is at h naught, what is your delta naught? It is just 8 lakh into pi, right? When x is equal to 0. And you can calculate the corresponding m naught, that we have calculated above. It is 4 lakh, right? This we have calculated. Now when we start increasing this x, this distance, the resonance condition will be gone, right? Because you see your phase difference depends on x here. So the resonance condition will be not valid, but it can again be valid at some other distance. When you move the plate to some other distance, then what is that distance? So how to calculate that distance? Any idea? So that distance will be reached when your phase difference, which is initially was this, so next phase difference, like delta 1, we just add 2 pi, right? 2 pi into it, so that it becomes this, correct? This pi is multiplied, okay? So don't get confused. So at this again you will have resonance, and it will go on, like you will get again resonance at 4 pi and so on, right? So yeah, and now you can solve this equation. So yeah, now you can solve this equation to find the value of x, right? So for example, what I am saying is, for delta 1 you can use, or yeah, you can solve it individually, or you can solve a general equation. So okay, let's solve a general equation. So what I mean is, your phase difference here is 8 lakh into pi 1 plus xh, and this should be equal to 8 lakh pi plus 2m pi, right, for different values of m. So when you solve it, so this cancel out here, right, and you will get this, okay, and from here you will get 250 into m, okay. So this is in nanometer. So you will get resonance conditions at which values? So you will get at 0, 250, 500, 750, so on, nanometers, okay. That means so if I plot it as a function of x, this transmittivity, so you will get resonance. So suppose 0 is here, 250 is here, 500 is here, so you will see a peak here, and then if you increase the distance you will again see a peak, then you increase the distance you will see a peak. So as you keep on increasing the distance between the two plates, at particular interval you will see a peak, okay. So this is the concept of interferometry. Now this is very useful. So how it is useful, that we'll see. Now one thing you might say that okay, above what we saw that if you increase the I mean you can change the frequency of the light also to get the resonance condition, right? Because you have, for different frequency, you have different modes of this Fabry-Perot parameter. So what I'm saying is, at a fixed distance, for different frequency, so you change the frequency by some amount, so delta mu, okay, you get you can get the resonance condition, right? And what is that interval that we calculated here? This is the interval, right? C by 2h. Okay, 2h naught. So what I'm saying is, resonance will occur again at the same distance, I mean at the same value of x. Okay, if you change your frequency like this, frequency of the light like this, so two things you can do, either you can change the distance or you can change the frequency of the light to get the resonance again. Okay, and corresponding to this frequency of light, you can calculate the you can again calculate the phase difference. But we know that the second the next phase difference where the resonance happens is this one, right? Sorry, this one. This you can also calculate using this frequency, using this formula here. You will get the same value. Okay, but now it corresponds to x equal to 0, right? We have not moved the plates, we have changed the frequency. And similarly, you can again change the frequency to 2 times of this or 3 times of this. As you keep changing the frequency, you will get delta equal to 4 pi, and this corresponds to 250. Right? Sorry, this also corresponds to x equal to 0. So we are not changing the distance, but if you change this to 2, 3, 4, you can have a resonance condition. So in general, you can change your frequency by some multiple of 2 by c by 2h naught to get resonance. Okay, p can be 1, 2, 3 and so on, and you will have same t by x, t versus x curve. We have same t versus x curve. Okay, so there will be overlapping of orders, and this quantity, this delta v c by 2h naught, it is called the free spectral range. Okay, so now you got the idea how to resolve two different frequency. Okay, so you have this much range Okay, I mean, so what I mean is, oh, we ran out of space. Okay, what I mean is, so suppose let me draw the t by x curve. Okay, so earlier what we are getting, at x equal to 0 we got a peak. Okay, then at x equal to 250 we will get another peak when we increase it. Okay, but and let's okay, let me change the color. Okay, let me write, this one was mu1, and then you will get the same, you will get the peak here and here. Okay, if you change your mu2, which will be equal to mu1 plus c by 2h naught. Okay, but the order will be different. So here this has order m equal to 0 and this has order m equal to 1. Okay, so there is overlapping of orders. I am talking about these two curves. Okay, similarly here you will have overlapping of m equal to 1 and 2 and so on. But now suppose instead of what is this value, c by 2h, if you calculate for h naught equal to 10 centimeter, it is we calculated above, right? It is 1500 megahertz. But instead of changing the changing the frequency by 1500 megahertz, what if you change it by, let's say, 300 megahertz? So now now I am plotting the same curve. Okay, so at 0 you have this peak and this. So where will the peak lie for where will the peak lie for mu1, let's say minus 300 megahertz? It will lie somewhere here. So this will be m equal to 0, this will be m equal to 1. Okay, you get the point.
Yes, sir, kind of.
Yeah, so this one was m equal to 0, m equal to 0, m equal to 1. So this was for original mu1, but when you change it by a value like 300 megahertz, it will shift. And then when you again keep increasing this 300 to 1500, they will again overlap like here. Okay, so they will be shifting and overlapping as you keep changing the frequency of the light. Okay, so now if you have two frequency of light in your incident wavelength and they are separated by let's say a distance, I mean a magnitude less than c by 2h naught. Okay, then they can be resolved separately. Okay, you will see two peaks instead of one peak. but the condition is that this, I mean, they should be less than this quantity. Now how less than this quantity? Uh, so there comes the concept of resolving power. Okay, so let me, let me go to fresh page. I think, yeah, at the end we have some page. So resolving power, so what I mean is, two peaks, we will call two peaks resolved. So suppose one peak is here at 0, okay, and another peak is here like this, okay. So if the intersection of their like if the, you know, falling intensity of this first peak coincide with the rising intensity of the second peak at half, like at 0.5, so here is 1, okay, we will call them resolved. This is the condition of resolved. At least they should have this kind of structure, okay. Then they can shift more and they will be fully resolved, but at least they should have this condition that uh, you know, this the falling intensity of first one should coincide with the increasing intensity of second one at t equal at I equal to 1 by 2, okay. This is the limit of resolution basically. So what I mean is, suppose the difference between them is, so this is the phase difference between the two resolved light, okay, and we know that this is the delta is given by 4 by under root of f, right. So for the first frequency or first spectral line, the delta we can write simply our earlier formula 2m pi, right. So let's call it delta 1, and for the second one we have delta 2 4 pi, and for h, because we increase the distance by delta h, let's see, and increase the frequency by mu 1, delta mu 1, this should also be equal to 2m pi. So mu 2 is basically mu 1 plus delta mu 1, okay. So suppose you have a light having two frequencies, okay, very close to each other. So this way they can be resolved, okay, and the resolving power formula is basically mu 1 divided by the difference of the frequency. So I am not deriving this formula, so you have to, you know, solve these two equations to derive it. The formula is, I mean, you get this. So it depends on the h naught, okay, the value, the distance between the two plates, the frequency of the first light, the coefficient of finesse f, and the speed of light. And you can also write in terms of wavelength. So just you know, so you know c by lambda is mu, so okay, you can write it pi by h by lambda 1. So this is the resolving power formula, okay. This will also be useful. But did you understand how which two spectral lines we will call resolved? This is the condition of the resolution, okay?
Yes, sir.
Yeah, they should be coinciding at half of the intensity, okay? If it comes more closer than that, then they will not be called resolved. So in the derivation, I mean, we assume that they are resolved and we derive this, okay? So the derivation I am not going through, but you can check any standard book. But this is the concept of resolution. Uh, so basically Fabry-Perot interferometer is used to separate separate the different frequency of light that are present in the incident beam, okay? So they are basically used to resolve different frequencies. So suppose you have sodium light, you know that sodium light has two very closely separated frequencies, right? So if you pass it through a Fabry-Perot interferometer, you will get two different peaks, like here, red and blue. Okay? And you can calculate the distance x here, and then you can calculate the frequency of the light, like both the frequency, the mu1 and mu2, using this formula. I mean this formula basically. So yeah, so let's solve some examples. So question on this topic are very simple. You have to use just 2-3 formulas. So let's see. Okay, do you have any question or doubt?
Not as of now, sir.
Okay, let's go to the questions. So I have not kept many questions, 2 or 3 questions. Let's go over them quickly. So calculate the minimum spacing between the plates of a Fabry-Perot interferometer which would resolve two lines with delta lambda 0.01 nanometer and lambda naught is 600 nanometer. Oh, everything is given here. See, the resolving power is given, the formula is given which I just wrote. Okay, so pi h root f by lambda naught. Okay, so what we have to find, we have to find the basically h, right? And this is straightforward, everything is given. We can calculate also the reflectivity is given 0.8, r is given 0.8. So we can calculate the coefficient of finesse, which is 4r divided by 1 minus r square. So 4 into 0.8, 0.32, 1 minus 0.82 square, 0.04, you get 8, right? Then you can put it in this equation. So lambda naught is 600, delta lambda is given 0.01, pi is 3.14 into h we have to find. H is the distance that we have to find, under root 8, lambda naught is again 600. So we can arrange everything, and so you will get, I am writing the answer, I have calculated it, you can check. So this is the distance that you will get. Okay, very simple problems, just you have to use this formula carefully. So it is writing here the minimum spacing. So h can be whatever, h naught, h plus x. So this distance we need. Okay, is it okay?
Yes, sir.
Yeah. Then next one. So a fabric period interferometer is designed with separation between the plates. So here H is given 2.5 centimeter. Reflectivity is given 0.8, again same reflectivity. So coefficient of finesse will be again 8, right? And if the slab is used in the vicinity of wavelength 546 nanometers, so lambda naught is given 546 nanometer. The highest order fringe in the interference pattern is, okay, we have to find the order m. So how to calculate it? Okay, so
Sir, that nu m into 2h by c,
uh,
and nu m we can find from delta.
wait, which one?
M is equals to nu m into 2h by c.
M is equal to, oh okay, yeah, that formula, yeah, this one, right?
Yeah, we used
Yeah,
earlier.
yeah, right. Oops. Yes. So mu m we can find by c by lambda 2h by c. So it's basically 2h by lambda, right? And yeah, okay. No. Wait. Fringe pattern. 2 into 2.5 divided by 546 into 10 to the power minus 9. This is 10 to the power minus 2, right? Can you quickly calculate it? 5 by 546 into 10 to the power 7. What do you get? I have not done this calculation. So
0.09 into 10 to power 7. 0.009.
0.009. No, but you need all the numbers because you have to multiply it by 10 to the power 7. What are the numbers after 0.009?
9157.
Okay. So it's C, yeah. Okay, cool. Okay, so then from the,
But sir,
okay,
what was the use of that R?
which R? Oh, yeah, the reflectivity. Yeah,
Yes, sir.
we'll see. There's another problem based on that. So here you have to calculate the half width. So what is the half width? And this is basically this delta lambda by 2, where the intensity becomes half. Okay, so this width we called it delta. No, this is basically half width. So this we have to calculate. So we know that this is 4 by under root of f, right? So half width is delta lambda by 2, so it will be 4 by 2 under root f, 2 by under root of f, which is 2 into root 2, 1 by root 2. What is 1 by root 2? Is it 0.0,
0.70
0.224,
something.
right?
No, 0.709.
0. Oh, wait. So, made some mistake. Reflectivity is 0.8, right? The coefficient of finesse that we calculated, mm, in terms of reflectivity is given like this, right? 4 into 0.8 divided by 1 minus 0.8 to the whole square, 0.32 and 0.04. Is it? It is 8, right? Delta lambda is 4 by under
4
root
into 0.8 is 3.2, right?
3 point. Oh, yeah, 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 sorry, yeah. It is 80, right?
Yes, sir.
Yeah, 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 yeah. Okay. So, yeah, yeah, it is 80. So you have, instead of 2 root 2, you have 20 here, right? Now what do you get? Now I think it will be 2 to 4. You can check. Okay, then we have to find the resolving power, lambda by delta lambda, which is pi h f by lambda 1. So you have everything. So the problems are very easy, just you have to remember the formula and how to apply them. 2.5 into 80 divided by 545. 545 is, it was right. 546. Yeah, you can calculate it. The answer will be D. Okay, so yeah, this was the last problem, but they are very easy. But you got the idea, right? About the Fabry-Perot interferometer. So it basically it is used to separate out different spectral lines present in the incident light. Okay.
Yes, sir.
Okay. So any other questions or doubts? So we will have our last session this Saturday. Okay. Yeah, this was the extra session. It was meant to be 1 hour, but yeah, it went longer. It's fine. Okay, so if there are no other questions, so then we can close the meeting today, and we'll meet you on Saturday. Okay. Okay. Thank you for joining.